Hello and welcome everybody. Today we are gonna talk about the IR spectroscopy applications in general, in scientific research, and the industry. The general use is well known to identify the functional groups in the compound, but it also used in scientific research in different ways, like identifying the optical isomers determines the rate of the reaction, which reaction is faster and why it's faster. Chemical stability studies the ability to resist a chemical change, and also in the industry used to identify the whole compound using a library database. We will talk about each one of these in details from research papers. In general, we can know if the reaction is complete or not by using the IR spectroscopy. In this example, the reaction is complete when the oxygen-hydrogen band disappears and the carbonyl band appears. So simple. It can also detect the positional isomers by comparing their fingerprint region and the geometric isomers by their band intensities. Let's see the research field. They identify the optical isomers. In this example, the configuration of the metal complex it changes the splitting of the cyanoband. It can be explained that the two cyano groups suffer the same environment, so singlet band occur. But with the other isomer, the two cyano groups suffer different environment, so the extent of stretching will differ slightly, so doublet band occur. Also a similar case with the anomers, but why it's important to know the optical isomers? In biological applications, some drugs with the S configuration are inactive drugs, while their R configuration is active, and vice versa. So we use chromatography to separate the two isomers, then using the IR spectroscopy to identify them. The second application is to determine the rate of the reaction. Here is an example of an I-click inorganic cycloaddition reaction, where the azide group reacts with the alkyne group through cycloaddition reaction to obtain a disubstituted triazole. So how can I follow up the reaction? Take a second and think about it. Simply, I can follow the disappearance of the azide group and the appearance of the carbonyl group with time, and both have pretty intense bands. So we will be able to calculate their rate constants. Let's follow the reaction together. Now the reaction starts. And from their IR spectrum, we can see that the azide group band intensity decreases with time and the carbonyl band intensity increases with time. Then calculate the rate constant. From these values, the complex which have the methoxy group have a higher rate constant. So presence of electron donating group increases the rate of the reaction. Using IR a lot can be done. It's a great tool. But you also need the spectroscopy mindset. Another technique can also be used. The fluoro NMR, because the product have fluoro but the starting material don't. The third application is the stability of a compound. Here is an example of a dicarbonyl complex. They want to measure its stability against the light. They followed the intensity of the carbonyl band. When the complex exposed to light, it decreased gradually with time. Because it will take some time for all the molecules to absorb it. Here the spectrum shows the dicarbonyl band intensities decrease gradually with time. The stability study can be against water, air, solvent, and others. It depends on your application. Now, in industry, they use the IR spectroscopy mainly to identify the compound by matching the spectrum with the database. If you are in a raw material quality control lab, you need to check that the material your supplier gave are the ones you ordered. So you check a small sample from them. That's for today's lesson. Hope you like it and good luck.